I would like to talk about a problem a caddis problem called build dependencies, and that involves Kahn's algorithms for creating a so-called topological sort of a directed graph, more specifically a directed acyclic graph. And in this video, I will also be discussing some input techniques and a technique for string indexing in Java. So let's talk about this particular problem here. Okay, so in this problem, you are given what essentially amounts to a dependency graph. Okay, so for example, in the sample input, you're given a number of files, such as a file called base and a file called gmp, and a number of dependencies. So for example, there's a file called q, and that depends on base. And there's a file called set that also depends on base, and set also depends on GMP. There's a file called map here that depends on GMP and it depends on base. And then there's a file called solution, and the solution file depends on these trees. So those dependency rules are given in the input. For example, it says GMP here, that depends on, it doesn't have anything that is incoming. Solution depends on set, map, and queue, which are these arrows here. Set is base and GMP, and so on and so forth. So this is a directed graph. Each of these files are nodes in this graph, and these arrows here represent those dependency relationships. And then the input gives us one file, in this case the last one, GMP, and it asks the question, what would happen if this file were changed? So in this case here, this were changed, and in this case, which other files that depend on it would need to be updated, would need to be rebuilt. And in this particular case, the answer to that is that if GMP changes, then of course, set would need to be updated, map would need to be updated, and then in turn solution would need to be updated. But these files over here, base and queue, would not need to be updated because it's not possible to reach them from GMP. On top of that, the problem asks you to output those that need to be changed in an order such that those that depend on each other, that the second one is built later. So here the possible orders would be GMP first, that has to be done first, solution has to be done last, but set and map could actually be done in either order, either like map set, but this could also be the other way around. So in this order, in the output, if there is a path from one node to another, then the node where this path starts from needs to appear earlier in the output than the other. And that in fact is called a topological sort. Topological sort. All right, so we will be talking about how to implement such a topological sort, and how to code this, what algorithm to use. Note though that this problem here also has two other challenges, right? The first challenge is that the graph here is only given implicitly. It is not given in terms of node numbers, like node, normally when we're given a graph, it may something like, 0, 1, and then we know that there's an edge from 0 to 1 or something like that. That's not the case here, okay? So we have to first convert those strings into node indices. And the second part is that in this problem, we are not asked to compute a topological sort of the entire graph, but really only of the subset of the graph that is reachable from the node that corresponds to the files that has changed. So in other words, here, we're taking the subgraph here of what is reachable from this one, and we only want to output a topological sort for this subgraph, not including nodes that are not reached or that are not changed in this case. Okay, so let's start coding the first part, which is the part to deal with the input in this case. Let me erase this part here and show you how to do that, because that's also a technique I think that you want to master. Okay, so in build tabs, I'm going to write this one in Java to show you the how to build an indexer in this case. All right, so our input here is the first one is n. This is the number of makefile rules. Okay, so this will be an integer n. Now here in this case, I will not be using a scanner. And the reason I won't be using a scanner is because this input here is line oriented. So in other words, I don't care about the different line boundaries. And in fact, there's nothing that tells me how many words appear on one line, right? I have to read until the end of the line. And in order to implement this, I'm using a number of Java IO and Java util classes. I'm gonna import these packages, and I'm gonna model this after the fast scanner that we usually use. So I'm gonna pull up the code of a previous problem that had this fast scanner, as you can see that here on the left. And specifically what I will be using is I will be using a buffered reader and a string tokenizer. Okay, so I'm going to create a buffered reader, and this buffered reader will be a new buffered reader, and it will wrap an input stream reader that is constructed from system.in. Okay, so on this one I can now call readLine and get the next line of input. So I'm going to call readLine. This will give me the next line of the first line of input in this case. And this first line of input contains an integer, and so I need to pass this integer. And so this would be integer dot parse int for this line. So this gives me n. Okay. So now this is the number of lines in the makefile. I'm going to write a loop from 0 to n. And now I'm processing separate lines. And the way I do this is by first reading a new line in this case. But to extract the tokens from this line, I'm going to use a string tokenizers. Okay, I'm going to use a new string tokenizer, and the string tokenizer is initialized with that line. This is code that you see here on the left in this fast scanner. I'm going to move that from now. Okay, so now I'm going to have to extract this. The first token that I'm getting here, next token, that is the part that is on the left-hand side. Actually, let me briefly download the sample data files in this case, so that we can see that. Okay, so that would be this file here. So you can see that, right? So GMP, that would be the first part. Okay, let me put this on the left, and I have this here on the right. Okay, so this token needs to be up, and this is going to be the left-hand side, right? But actually, left-hand side there is a colon at the end, so I'm going to strip that colon out by using the length of this -1. Okay, so now this is a string, but it should really be a number in a graph. And so what I'm going to do is I'm going to say this node here should be should be indexed, right? It should be numbered. So I'm going to say indexer dot index, okay, index LHS. So what is this indexer thing here? Okay, so this has to be something that allows me to put in strings to get out an index. Okay, so I'm going to say indexer, and I'm going to need a new indexer here. And so let's implement that. Okay, so what does an indexer do? How does it work? And how do I implement it? All right, so it needs to support a method that returns an index, okay, given a string s, okay. And these indices, they will be stored internally in some kind of hash map where we can put a string in there, we get an index out, okay. So we'll call that, I'm going to call that the index, right, which is really what that is. And so when the string is being indexed, okay, then what we do is we'll look into that index and say index.get and see if we already know about this string. And let's see if that the index would be I. Now, if it's already in there, okay, so then if let's say then this is what we return. But if it's not in there, then if this is not, we need to put it in there. So index put s. Now what are we going to put in there? We're going to put the next available number, and we're going to call that n. We're going to increment that number here, and this is also the number that we will return. So we're going to put an int n. This is like, number of strings currently indexed. Okay, so this is how you implement the index. And what did I forget? And I of course need to initialize this. Otherwise, it will give me a null pointer exception. So this node would now be indexed. Okay, and now I need to read the remainder. So everything that follows here. For example, solution set map q. I would do this with a loop. So say while the tokenizer. I'm going to call this tokenizer. So while the tokenizer has more elements, right, I'm going to need to get the next element out there, u, and so this would be with next token, and of course this needs to be indexed with the indexer. Right? And so now I have an edge in the graph. The edge goes from u to v in this case. And so I need to add this to the graph, and for this I'm going to need to have my graph representation, and as always I'm going to use an array of integers. Now fortunately in this problem they actually give us how many nodes there are, so I'm going to put this here, and I have to initialize those again in the usual way. Okay, so now we can add this edge to the graph here in this case. I'm going to say adjacency of u is equal to v. Notice that the graph here is given in the opposite. So if the left-hand side depends on the right-hand side, but the edge goes from the right-hand side to the left-hand side. After having done this, so we have the graph. Let's see if we can, if this already works. We're going to say arrays to string adjacency and compile this. And this did not work because the call is called add. And in this case, also since this throws IO exceptions, just show the exception or IO exception for main. And so let's run this, and here we get a graph. That is our graph here encoded with the indexer. All right. So now let us implement the next step of the problem. Before we do that, there's actually one more input, and this is our start node here. Okay, so let's read this. We're going to have to read a line with this one in here, and let's maybe put I think this line should actually have this the last one. This is the start one. I'm going to say index int start, and I think this would be indexer.index of get line. Let's see if that works here. The start is in this case 0. That was the very first one. Okay. All right, I want to suppress those warnings. All right. So now in this problem we have two parts. Before we can deal with these dependencies, we first need to find out which nodes are actually reachable from that start node. And to do this, we implement our traditional DFS search, right? So I'm going to do a Boolean array. I'm going to call it reachable. It's a new Boolean array with n elements. I know that reachable of start is that is true. I'm going to need a DFS DAG. I always call it DFS. It's going to be an array DAG. And I'm going to do the DFS. So while DFS is empty, I'll be pulling from that queue, maybe with pop. And so this would be one node u, and then we're looking at all the neighbors of u, and if those neighbors are not already reachable, then we will mark them as reachable, and we will also schedule them for exploration. Right, so reachable is true, and we will schedule them. So with DFS dot push. And of course, at the beginning, we got to bootstrap this process by pushing the start state onto the queue. All right, so now we have done the DFS, and now all the nodes that are reachable should have this reachable bit set. Okay. So now comes the part where we need to output all of these reachable nodes in topological order. Okay. Let's talk about how to do this here for a second. The algorithm is actually a very simple algorithm, very intuitive. Okay, so it's credited to Khan as referred as Khan's algorithm. Okay. Um, so the idea is we want to find this topological order. So we want to make sure that in a directed acyclic graph, let's say we have a node here and then maybe another node here, and somehow there is a path from A to B, okay? And if there's such a path, then A must appear before B. So there's A, then something else maybe, and then B. Okay, this needs to be ensured. And so with this algorithm works as follows, in that it first looks at those nodes that don't have any incoming edges, right? So the directed acyclic graph would typically look like this. You have some nodes here that don't have incoming edges because the graph maybe goes like this, goes like this, and then maybe it continues, right? So these graphs obviously have some nodes that don't have any incoming edges. And in fact, they also have at least one sink that doesn't have any outgoing edges. So we need to find those nodes that don't have any incoming edges. And in fact, what we're going to do is we're going to create a data structure where we keep track of how many incoming edges each node here has. Okay, I'll call this incoming. Okay, so incoming, and this is a kind of also for one of for each of these nodes. Okay, so let's go and let's count those. Okay, so we're going to go through each node. Okay, and then for each node we're going to go through its neighbors. Okay, so these are the nodes U. We're going through the neighbors, and so here we find an edge UV, right? Okay, so UV, that means that that the number of incoming edges to V is greater than 1, so it's increased by 1. So we count those. Now we need to look at exactly those nodes that don't have any incoming edges. And those nodes we will again be placing into a queue. Okay, I'm going to create a queue, and we're going to call this, I'm just going to queue. Okay, so this queue is also an array deck. And I'm going to put all of these nodes that don't have any incoming edges this into this queue. So I'm going to go through all the nodes after I've determined the number of incoming edges. And if a node doesn't have any incoming edges, so if this is equal to 0, then I'm going to put this one into this queue. Because I know that those that don't have any incoming edges, those are ready to be output right away. They can appear in the output, in the topological output, because nothing has to be before them because they don't have any dependencies. So now the idea behind the algorithm is as follows. Okay, so if I have this graph, let's say with these nodes here, and maybe this is node A, this is node B, and then just to pick an example, maybe this is node C, and then maybe this here is node D, then I would try to close this. So then I would, sorry about that. Oops. So then I would say, okay, these don't have any incoming edges in this case. So that means they can be output, right? So A can be output, B can be output. Now then what happens next? So with A and B being output, right? So at this point here, they can sort of be logically removed, right? So at this point, C no longer has any incoming edges. So now C can be output. Then I can remove C, and at this point, D would no longer have incoming edges, and I can output D. So the idea is to always keep track of those that have no incoming edges, output those, and then remove them. We're going to remove them not actually from the graph, but virtually. We're going to remove them by decrementing the incoming count of all the nodes that they reach, as if this edge didn't exist. Okay, and if this adds a new node to this queue, then that is what we'll do, right? Okay, so let's try this idea. Okay, so while we still have anything in our queue left, okay, so while this queue here is not empty, we're going to um, um, pull a node from the queue. And here the queue order actually doesn't again doesn't matter. It's just a list of things that we have left to do. Okay, so this node u, we pull that from the queue, and so this can now be output. Okay, now in our particular problem, I want to just make a comment here. I'll put u. I'm going to return to that in a second. Okay, so then we go from here. We go out to all the successors of this node. Okay, and all these successors essentially now going to pretend that we have removed u from the graph, that the edge UV no longer exists. And so what this will do is will actually decrement incoming of V. Now, if at this point V has no longer any dependencies, okay, so if this is 0, then actually we are able to logically remove V as well. So we can offer V to the queue, right? And so this is the entire algorithm actually. Okay, so if we do that, if at some point we don't find any nodes, if all the nodes that have no incoming edges have been processed, then we either done, or if we don't find those, it might mean that the graph is a cycle. But here in this problem, that would not be the case. So here, in actually, we would say, if all nodes have been output, then great. It's a DAG. If any are left, okay, cycle, right? So now going back to our problem here. So this node here that we are finding. First of all, this finds this topological sort for all the nodes in the graph. But the problem only asks us for that subset that's reachable from this node. So we're only going to output it if it's actually reachable. So if this is reachable, this node here, u, then we're going to output it. Now we're going to output this, but what we're supposed to be outputting is actually, we only have the node number, u, okay? So we need to ask our indexer, and we need to say, okay, what's that u? So we haven't actually implemented this yet. I'm going to say indexer, and I'm going to call it, in this case, I'm going to call it list get of u. So our indexer also needs to have a list of the strings that it has indexed in the order in which they were indexed, okay? So let me add that to the indexer here. Okay, so if something is being indexed, okay, then we're going to say list dot add this string s, and we're going to need to have a list of these strings list that stores those strings. So we can go both ways, right? Um, we can go from the string to the index, and from the index to the string. And this is what's being output here. All right, let's try this out. And let's see if we can run this. And in this case, the output was supposed to be GMP. We output set map instead of map set, but again, both of these outputs would be possible. And so let's see if this already was it. Let me remove the debugging output here and, and test this one more time. And then let's see if we can actually get this submitted. And so here, I think for this problem, the time dependencies were pretty generous. So we may not be timing out because of I/O slowness, I think. Okay, it seems to be running, and it looks like this problem was accepted here in this case. So here, I did not need to optimize any output um, because of the generous time bounds. So in summary, what I've shown here is how to do line-based input with buffered reader. I've shown you how to implement an indexer, and this indexer is a class that you can reuse, right? I mean, it supports an index method. You pass in a new string. If it's not in the index, it's going to be added. If it is, you just get the number and a way from the index to go back to the original string. Plus, you can also find out how many have been indexed. If you have problems where the number of nodes in a graph is not known until everything has been indexed, you can use this n to create the graph in this case. Although in those problems, you're not able to index and update the graph. Here, this problem was a little bit on the convenient side because the problem actually guaranteed that there will be exactly n nodes in the graph, and so we were able to pre-allocate those adjacency lists before we read the input. Then I showed you how to do, in this case, a DFS to find those nodes that were reachable and to perform a topological sort that output those nodes that were reachable in topological order. So topological order means if a path is from A to B, then A will appear before B in the input. A few more things about topological sorts. So in competition problems, very often, so it's rare that you find something that is like this, where they just ask you to implement it. In fact, this was a practice problem. I don't even think that was a real competition problem. Some variations that we have seen. Okay, so in some cases they may ask you to essentially determine if there's a cycle in a graph, right? And if there is a cycle here, then you would determine this if at some point you would run out of nodes that don't have any incoming edges. So for example, the simplest case is if you have a graph that looks like this, right? It has a cycle. Here you couldn't even get started, right? I mean, at this point, none of the incoming counts would be 1 and 1, and you couldn't even get started with that queue, right? So clearly there's a cycle. But if you had a graph, like that were like this, you would start with this node, and at this point here, you would run out of nodes with no incoming cycles. That's one variation that we've seen. Another variation that we've seen is that they may ask you things like, "Oh, is the topological sort unique or not?" Right? Is there more than one choice? And in this case, this boils down to determining whether there are multiple nodes that can be pulled from that queue. Because here, at this point here, really, it doesn't have to be a queue. It's just some working bag of things we can put in and pull out. This really could be any. Okay. And in this case, we know that if there's more than one choice, this would result in different topological sorts, right? So if you have like A, B, C, D in this case, then the topological sorts are A, B, C, and D, and A, C, B, and D. And that depends on after we've removed A from the graph, then both B and C are in that queue. We could pick any, right? And so to determine whether the topological sorting is ambiguous or not, you would need to look at how many elements are in the queue at this point in time.